Okay, let us try to find the length of a curve. Let me bring in some geometry here, and then we will use this curve here to discuss our topic today. Okay, so this will be the x-axis, y-axis as always. So let's say we have a function here. This is our f of x function. And then what we want to do, we want to find the length of this curve. Maybe let us say from maybe some point A somewhere here, say up to some point B, which is far somewhere here. Okay, so previously we had discussed how to find the area, this area here, below the curve f of x, the x-axis, and these two lines here, which is the x is equal to A and the x is equal to B. So we know how to find the area. So what do we want to do here? So we want to find the actual length, exactly the length of this curve that we have here, from the point A up to point B. So we want to say how long is this? So this is what we want. So we come to this situation here where we have to find the curve, the length of some curve. We come with the knowledge of only how to find the length of a straight line, and that is the only thing we have, and we are hoping that we can use that we know to find the length of this curve here. And yes, we can do that. We can actually apply the concept from the straight lines into curves. And how do we do that? We achieve that by zooming. Okay, so by zooming. So for instance, if we come to this line here, this f of x line, and then you try to zoom, you take a small space here and you zoom it, you go down deep into it. There is a place where you really find that this curve actually look like just a straight line. Just then if you reach that point, then what you then do is that you then try to find the length of at least this line here. So of course, since it's not the whole value of this f of x from A to B length, so we can name this a delta s, for instance. So our s is actually what will be giving us the full length. So this small piece we will put with a delta. It's just a small value that you have here. Okay, so this we achieve by zooming. So why are we zooming like this? We are zooming because we want to use the Pythagoras theorem. So according to the Pythagoras theorem, the value of this line here will be equal to, so this delta s will be equal to what? According to the Pythagoras, it will be equal to some square roots, and we need two values which we can put power 2 here. And what are those values? Those values will be delta x value, and then we also need a delta y value. So this is how we'll get the small s value here, right? So then the delta x, again, as you know it, delta x will be power 2, delta y also will be power 2, right? So this is the small value. We need to get a lot of these small values, and then we need to sum them at least to get an approximation, because of course, since these ones will be discrete values, they will not give us the full version of the answer, but at least it will only be an approximation, which we then will have to improve on to actually get the right value. Right. So how does this go? So basically what they do to apply this Pythagoras to this is simply a matter of just taking this line and just break it into some small portions. Let us say maybe, for instance, say we start from the beginning here, then we do a small chopping, maybe we do another chopping, then we do, for instance, another chopping, maybe say is up to this point, another chopping, etc., 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 etc. Maybe say up to the end. So this one up to the end where we stop here, right? So this, for instance, could be maybe say 0.1. So this is 0.2. So this is 0.3 and 0.4, etc., etc., etc. Say this is Pn, right? So this is Pn, far away. Okay. So as we break, so what happens is that we get corresponding x values, corresponding x value, for instance, here. So this, it happens right through up to this place where I skipped. We have a small value here, and then the last one. So let us actually put the naming here. So say, for instance, this is x1. We are moving from x0, x1, x2, dot, 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 up to say this is xn minus 1. Then let me write this one here, xn. So xn corresponded to this value down there. Right, so after we have this chopping, these delta s, where are they? So these delta s values is therefore means these delta s values is the values that you have sitting here. For instance, this will be this delta s value. This will be our delta s1, for instance, right? This red line here, this will be our delta s2, for instance, up until, let me write it outside here. So then here we'll have a delta Sn, right? So this is what we get. And all of these delta S values, delta S1 up to delta Sn, they all share this one representation here. So they are actually given in terms of the Pythagoras theorem. So ourselves, since we want to find this length then from A up to B, so what we do is we have to sum these delta S values. So let us do that. Is therefore what we means we have here. It means we're having a delta S1, so plus delta S2 plus etc., etc., up to the last one, up to say delta Sn. Right, so we can have a better way of writing this. Of course we can do that. So when we do that, we can actually bring the sum notation. This is how we actually represent the summation. Then let us say this is I is equal to 1 up to I is equal to n. Then what are we summing? We are summing this delta Si, right? Okay, so that is what we are summing. So to get a better approximation, because really with this notation it means we are actually having only the approximations. So what will improve this approximation that we have here, the approximation will improve if we reduce this interval. So the more we reduce these intervals here, this we get able to capture more values of the length of this curve, so we get close into the actual accurate value, right? So we actually get close to the say full value of the answer, so we get something better. So the way we can actually get the ultimate beta value of this length is through trying to find the limit as n tends to infinite. And then what is this limit for? The limit, right? So it's the limit of these delta Si values, okay? So we want to get as many as possible of these delta Si values, right? So but what happens that with calculus, once we have it like this, so now we have this limit as n tends to infinite of this. According to the knowledge in calculus, once we have a limit tends to infinity like this, it allows us to replace this with the integration sign. Okay, so right, so when we do this replacing with the integration sign, then the I that's lower index there, it must go away, and then also the delta must go away. Okay, so before we actually replace, let us try to redefine this, write it in a different form. So let us do that. So this is equal to the limit as n tends to infinity, right? So I is equal to 1 up to n. Then this delta s I, so we know this is a Pythagoras formula here. So therefore we just put that. It means it's the delta, therefore xi power 2 plus delta y I power 2. Right, so this is what we have. According to the mean value theorem, so what we have is that the mean value theorem tells us something special about the slopes between the curve and the straight line. Okay, from the mean value theorem, so what we know is that in the interval between every small interval that you have here, right? So the mean value theorem tells us that there is an x value where the slope is equal to the slope of the straight line, right? Slope of the straight line, slope of the curve and the slope of the straight line, right? So what this gave us, it gave us a way to be able to have a substitution for this delta y, which we have here, because then this delta y will be equal to delta x times f prime of x, right? So this is what the mean value theorem tells us, and this will be happening. So this x star here is basically, maybe say, to make it general, up to xn, right? So for all these infinitesimal small subinterval, the theorem says this exists, of course, provided the derivative is able to be obtained there in that location, or say we have the function is continuous, is also differentiable, then we have this statement. Right, so just continue. So it therefore means we can be able to rewrite this value of delta y. Just do that, trying to do that. Delta x I squared. So the delta y we can replace with a delta xi. I will put I now to match what we have here. Then it's a times f prime x star, right? Power 2, right? So therefore, as we try to simplify this further, so this will be the limits, then tends to infinity, I equal to 1, then our square root. So what we see is that the delta xi is common, so we can write it once. So therefore, this will leave us with the 1 here, plus then the function f prime star, and this is power 2, then 1 delta xi power 2, right? Then lastly, what we'll say is that the limit as n tends to infinity, right? As n tends to infinity, I is equal to 1 plus, put in the bracket here, power 2 times delta xi outside now. So this one is outside, so the square root ends here, this delta xi is outside. So what it means that what you have now is that we have just shown you that the delta si that we started with here, it can be written as this could be the right hand side of the delta si is equal to this. So now when we reach this step, we are ready to replace this limits as n tends to infinite. We are ready to replace it with the integration sign, so we can do that. So it therefore from a up to b, then we continuously sum all the values of this square root function, which is a 1 plus f prime of x power 2. Now with the integration sign, the delta again will go away, the I will go away because I is for discrete values, so we're no longer having discrete now, so we are changing to continuous. So we now just are continuously summing, so do also this star that we have here, so it will go away. So we just are having f prime of x now, as we can see here. So now the delta will be replaced by just a dx. So this that we have obtained here, so this is the formula that we'll be using in this section when we try to find the length of some curve f of x. So this is what we'll be using. Alright, I'm trying to cycle it nicely. So this is what we have as s equal to this integral sign. Okay, so the next thing that we have to do now is we have to use this formula to solve some problems which require us to find the Arclength. As you can see, this one is with respect to x. So there may be cases where we have to find the Arclength with respect to y, so you simply just change the variables. There will also be cases where you find that you are facing a parametric equation, and then you just have to adjust accordingly. Maybe let me erase and write that so we see it. Let me go back, and I will try to clear the space here. Right, try to clear the space. In fact, we have even discussed this. Maybe let me just clear everything, then try to rewrite afresh and write a neat and write it neatly now. Try to clear everything. Okay, so let us say we have a curve. So a curve like this. I'm bringing back that curve that we had here. So we said we are from A up to B, and we want to find this length of the curve here. So as we just have seen, we have said the length of this curve S is equal to the integral from A up to B, square root 1 plus f prime of x. So let's say f prime of x power 2 dx. So if you are facing a parametric situation, so for the parametric equations, I write it here, the parametric so what will happen is that this formula will be A up to B. Then remember there was a delta S here, a delta X. So this delta X over delta T, for instance, this will give us a dx over dt, then all the rest to power 2, where there was a delta y. Remember, there was delta y here. So if you divide by delta t, for instance, say they are both functions in terms of time. So maybe say this is x of t. Maybe say this also is a y of t. Then their derivative will come and sit into this square root here, of course raised to power 2, as we are doing here. So therefore this delta y, delta t, now with under the integration sign, so this will be dy over dt all power 2. Therefore the most independent variable, which is t for this case. Sometimes it will be theta. So if you're facing x theta, y theta, therefore you'll be having dx over d theta power 2 plus dy over d theta power 2 into this square root, integrating with respect to theta. So you simply adjust according to what is your most independent variable of the two, say between the two functions, because for parametric equations they will have a common argument. So you check what is the independent variable, and that is what you integrate with respect to, and of course you differentiate with respect to that. Right? So I guess we have all the formulas we need for this recording. So let us try to solve some problems. Okay, so this will be our first exercise. Okay, I will not write everything. I will just write what is important, the equation and the limits, and we just solve it. I will do that for all of them. So let us start with this one. So here the curve that we have is y is equal to 2 over 3 x raised to 3 over 2 plus 1. And they say we must find the curve of this function here from x is equal to 0 up to x is equal to 1. Right? So let us do that. So the formula we're using, it need the first derivative. So let's try to find the first derivative here. Is equal to 2 over 3. Of course, 3 over 2 means it's a x. 3 over 2 minus 1. Therefore, it's 3 minus 2, which therefore it's a 1 over 2 here. Right, so this we can see it simplifies to x raised to 1 over 2. Right, so s is therefore equal to 0 to 1. Therefore, the square roots accordingly, as per the formula tells us what to do. Therefore, the derivative 1 over 2 here raised to power 2 with respect to x. So therefore this is equal to 0 to 1 square root 1 plus x dx. So luckily it's an easy exercise. In most cases, integrals under this section, they have some problems, but of course the ones we sometimes have to solve, as you can see, they are easy. But this is because they prepare these ones to be easy when we solve them. Mostly just in a general case, because of having to differentiate, having to put that power 2, having that square root at the end, things sometimes get complicated. But again, this is an easy exercise. Okay, so basically what I'm saying is that when we are solving problems under this section, you just have to be, just expect anything. So this one is the easy integral. So how can we solve it? Let us use u substitution. Let u is equal to 1 plus x. then the derivative means is just equal to dx. So therefore this is equal to, so 0 to 1. So u raised to 1 over 2. 1 over 2 and that square root sign is the same thing. So therefore du, so therefore the answer will be 1 over 2 plus 1. It means it's 1 plus 2 is a 3 over 2. So therefore we are having 2 over 3 here. We substitute back the x values, but you have an option to maybe redefine your limits according to your u value. So what I'm doing here, I'm just going back to the x. So therefore here is a 3 over 2. Right, can go down. Right. Okay, so the limits will be 0 to 1. 2 over 3 will be common as we apply the limits. So therefore to be 1 plus 1, this is 2 raised to 3 over 2 minus x is equal to 0. So we left with 1 there. So therefore is equal to 2 over 3. Therefore we have a square root with the 8 minus 1. Okay, I'll leave my answer here. Okay, so right, this will be the first example. Just quickly try to do another example. Okay, so this is number 2. Again, I'll just write the equations. So now this exercise I have here, they have parametric equation. So let me write it. They say x is equal to e raised to minus t cos t. Y is equal to e raised to minus t sine t. Right? So they say find the length of this curve coming from this parametric equation. So that's what they say. And then the interval is from 0 to t is less than pi over 2. Right, so we are facing a parametric equation situation. So I think as you saw from the formula, we have to find the derivative of this y and the x. Then we put them back into the equation, that formula. So let us do it outside. First get to the dx, dt one. We are facing a product situation. So this will split into 2 terms. So it will be minus e raised to minus t cos t, therefore plus, therefore e raised to minus t. Then derivative of the cos, it's also have a minus sine t, right? Maybe we can simplify a bit. So minus seem to be common. Exponent is also common. So this leaves us with the cos function on the first term, therefore plus the sine function on the second term. Right, so let me use the space here to get at the dy dt. It's a product also with the minus t sine t here, so it's a plus e raised to minus t. Derivative of the sine function, you know it's a cos function. Simplify a bit, the exponent is common again. We have a cos which is positive, let us start with it, minus sine function. Okay, so just we have to put it together with the power 2, each with power 2. Let's do it here. So it's a dx over dt all power 2, so it's a plus. dy dt all power 2. Right, so what do we do? So here, even if you're having multiple terms, what you need to do is you put 1 power 2 once. You don't say power 2 per term. No, you put everything inside, then you put 1 power 2 outside. Then you may have to expand if needs be. So here we're therefore having a minus e raised to minus t cos t plus sine t here. So it's a plus. Again, we want to put 1 power 2 outside. Therefore, it's e raised to minus t. Then it's a cos t minus sine t, right? 1 power 2. Okay, so we apply the power 2 and see what you get. So minus will be gone. The exponent will take e raised to minus 2t. So we have a cos and a sine, all the rest to power 2 in that bracket. So this will have to open it. So this will be cos squared t plus the middle term, which is a 2 cos t sine t plus the last term, which is a sine squared t plus. So the exponent, because the power 2 applies to both of these brackets, so it applies to this exponent, it applies to these brackets here. You know this high school stuff. It also applies to this bracket. Right, so therefore we're having minus 2t again, so it's a cos squared t minus 2 cos t sine t, right, plus sine squared t. Okay, so the exponent is common, as you can see. So you can see the exponential function. It appears in both of these terms. So we can write it once. So let us do that. So this will be e raised to minus 2t. Then we open up all of these brackets. So the cos squared and the sine squared here, as you can see, this will give us a 1. So this will give us a 1 plus. Again, what you see also is that the cos squared and the sine squared here, we get another 1 from there. Let me write that. Sorry. So there's another 1 from there. And then another thing that we see is that the 2 cos and the sine, there is a minus here, same value. So this one is gone. So we therefore just are having, so it means what we have here. So we have a 2 e raised to minus 2t. Right. So we continue. So now we bring back the formula. Okay, so we bring in the formula from 0 up to where? To pi over 2. So it is the square root. Maybe I can even make it small now. There is nothing much inside it. It's just a 2e minus 2t. This is equal to pi over 2. So we're having a square root 2 here, which is a constant. A raised to minus t dt. So the square root, as we know, is the same as. So therefore this power 2 cancels out. So the power 2 cancels out here, so giving us e raised to minus t. So that's why we having this there, right? So therefore square root 2 is outside, is a constant, raised to 1 pi over 2 e raised to minus t dt. Therefore we know now we have a square root 2. So the integral, the exponent will come back as this, divided by this minus 1. So therefore it will be minus here. Then our limits 0 to pi over 2. Right, so erase here. So this is equal to minus square root, which will be common as we apply the limits, e raised to, so t is a pi over 2 now, we are substituting, e raised to 0, still 1. We allow the minus sign outside here to be absorbed and go inside the bracket. So this will be square root 2, 1 minus e raised to minus pi over 2. Right, so I will stop here. I think this is the answer. I think it was an easy exercise. I think the two problems that we have just solved, they give us an idea of what do we do if we have to find the length of a curve. So we just showed where the formula comes from, and then we applied the formula to one f of x function and one parametric equation exercise. Okay, so I think you can just try to do more. Myself, I'll stop here.